Down in the dark, a fish hits a lure. That impact is a violent kinetic event. It generates a high-frequency shockwave that races up the braided line at incredible speed. For decades, the fishing industry has sold a very specific story about what happens next. The claim is that if you buy a rod made of 40-ton high-modulus carbon, you will feel every single twitch. They equate raw material stiffness directly with sensitivity. Physics tells a different story. True sensitivity has nothing to do with how stiff a rod feels in a showroom. It is strictly a measure of vibration transmission efficiency. It's about how much of that original kinetic energy survives the trip from the water to your hand. In engineering terms, a modern fishing rod is a mechanical waveguide. It is a highly structured hollow path designed to transport elastic strain waves from the tip of the rod straight down to the base. There are two ways to build this waveguide. You can mass-produce an industry rod that prioritizes glossy aesthetics and heavy hardware, or you can build a physics-optimized rod, engineered specifically to protect the structural integrity of that incoming wave. The difference between landing a trophy catch and missing a strike entirely doesn't come down to a carbon rating. It depends on whether that physical signal can survive the gauntlet of the rod itself. That survival test starts at the very tip of the rod. Because the tip has the smallest diameter and lowest mass, any physical weight added here acts as a massive inertial multiplier. It is the first checkpoint where the wave is either preserved or immediately compromised. We can measure this destruction through a metric called blank recovery speed. This chart plots how long a rod's tip oscillates after being loaded. A perfectly optimized rod has a fast recovery. It snaps back and returns to a dead stop in under half a second. A heavy, poorly built rod suffers from slow recovery, wobbling back and forth for over a second and a half. That lingering wobble is a parasitic energy sink. When the tip is busy vibrating from its own excess weight, it creates a massive mechanical noise floor. If a subtle strike registers while the rod is still oscillating, that tiny data spike is entirely buried. You could have the most expensive, rigid carbon fiber on the planet, but if a manufacturer weighs down the tip with heavy thread wraps and bulky guides, that stiffness becomes entirely useless. Adding just a few unoptimized grams to the end of a lever creates an inertial dampener. It blinds you to the microscopic vibrations in the water before the signal even begins its journey down the blank. If a wave does manage to survive the tip of a standard industry rod, it enters the midsection. Here, it crashes directly into the hardware. This introduces a structural dynamics concept known as mechanical impedance mismatch. Mechanical impedance is a material's resistance to motion. When a wave travels through a uniform material, it flows cleanly. But when it hits a boundary between two materials with wildly different densities, a portion of that wave's energy is forcefully reflected backward. Look at the thick, glossy coats of cosmetic epoxies slathered over the wraps of a standard rod. These dense chemical blobs might look good in a store display, but physically they act as acoustic barriers. They absorb and kill high-frequency vibrations. Right underneath that epoxy are heavy, dual-foot stainless steel guides. These create rigid dead zones along the flexible blank, acting as physical roadblocks that further disperse whatever kinetic energy managed to push through the resin. With every mismatched boundary the signal crosses, it loses power. The vibration reflects, scatters, and eventually bleeds out its energy as it crashes against the heavy, cheap materials. Mass-produced rods engineer the sensitivity right out of the carbon fiber. They suffocate the physical signal under components designed for showroom aesthetics rather than physics. Now let's track a wave entering the tip of a physics-optimized rod, where every millimeter is designed to preserve the signal. It starts with the foundation. Instead of using a traditional fiberglass backing to maintain the tube shape, this blank relies on a scrimless carbon architecture. By weaving microfine slit fibers directly into the primary carbon layout, it maintains massive structural hoop strength without adding dead weight. The roadblocks are gone too. Heavy steel is replaced by ultralight single-foot titanium guides, secured with microdoses of low-viscosity epoxy that penetrate the threads without creating a thick, dampening boundary. This diagram illustrates perfectly matched mechanical impedance. Because the density of the carbon, the minimal epoxy, and the titanium guide are carefully aligned, The wave glides through the node with 100% transmission efficiency, zero reflection, zero energy loss. By ruthlessly stripping away parasitic mass and matching the impedance of every component, engineers transform the rod into an uninterrupted acoustic highway. It delivers the strike's raw energy directly to the base. That preserved wave now reaches the end of the carbon blank and enters the handle and reel seat assembly. But the mechanical system doesn't end at the rod. The human hand and arm act as a viscoelastic boundary, a biological system that introduces its own highly variable impedance to the equation. If you wrap the rod handle in massive grips of EVA foam, that soft material acts like an acoustic sponge, soaking up the high-frequency elastic strain waves before you can feel them. Conversely, rigid materials like raw cork or woven carbon fiber act as efficient, low-attenuation waveguides. When paired with an optimal split-grip design that exposes the bare carbon, the kinetic wave bypasses the intermediate materials entirely. It travels straight into the dermis of your fingers, violently triggering the microscopic mechanoreceptors in your skin. High-modulus carbon is ultimately just a raw ingredient. True sensitivity is a delicate, highly intentional system of mass reduction and preserved wave mechanics. An angler shouldn't pay for the illusion of stiffness. You are paying to remove the physical barriers between your hands and the unseen world beneath the surface.